Before starting with the sphere, let us have a look at the circle. The circle is the set of all points in the plane with the same distance r from a given point M. This means the given point M is the center of the circle and r is the radius of the circle. Well, how can we calculate this distance between the point M here and the point P on the circle? Well, either we use here the Pythagoras or we just use the vector MP, and think for yourself, what is then the square of this distance? Stop the film, write it down, and what does it equal? Stop the film now. And here comes the result. The squared distance can be written as the difference of the x-coordinate, so x minus xm squared, plus the difference of the y-coordinates, y minus ym squared, and equals now obviously to r squared. So this is the equation of a circle. Any point on the circle fulfills these conditions. Its x-coordinate and its y-coordinate fulfill this condition. Let's look at some examples. In example 1, we're given a circle by its center and a point on the circle. And we want to find the equation of the circle. Try it on your own. Stop the film now. And here comes the solution. Since M is the center, the equation of the circle is x minus 5 squared plus y minus 3 squared equals r squared. Now we have to find r, so we can either find it by finding the distance between M and P or by inserting the point P into this equation. It both ends up as the same equation. And solving this, we get r squared is 25, so the radius is 5, that was not asked for, and the equation of the circle here. Read example 2 and try to solve it on your own. Stop the film now. And here comes the solution. The point A with x-coordinate 13 lies on the line, so let's find its y-coordinate. From the x-coordinate we see that t is 1 and we get y-coordinate is minus 10. So point A has coordinates 13 minus 10. The center of the circle lies on a normal line to the line L through the point A. Let now d vector with components x and y be the direction vector of this line n. Since they are perpendicular, the scalar product of their direction vectors is 0. We get 5x minus 12y equals 0. Well, the simplest way to set that equal to 0 is by choosing for x the 12 here and for y the 5 here. So we get x equals 12, y equals 5, and the direction vector of the normal line is 12, 5. The length of this direction vector is 13, and we want this distance to be 26, so we have to use twice this direction vector. And it can be plus or minus times 2 times the direction vector. So we get two solutions, one for plus 2, so 13 plus 2 times 12 plus 24, minus 10 plus 2 times 5. We get this point, central point, and hence we get this circle. When we use minus 2, we get the result down here. Have a look at example 3. Think about how you would solve it, and then watch the solution, so stop the film. Let us find first the equation of the circle. Let's solve that for y. So we subtract the x minus 2 squared. Now we have to take the root. And now remember, when we take the root, we always should make here plus and minus. Now, if we don't do plus and minus, we have only plus here, which means we get only the upper part of the circle. We get only when the y minus 3 is positive. For the y minus 3 negative, we would get the lower part of the semicircle. We only want the upper part, so we'll read away the minus. Last step, let us add 3 here and expand this expression on the root, and we get this here as the function equation for f. Now let us look at the sphere. The sphere is the set of all points in space with the same distance from a given point M. So M is the center of the sphere and the distance r is the radius of the sphere. Now let P be an arbitrary point on the sphere. So the condition that lies on the sphere is that the distance MP is r. We can calculate this distance like before using the Pythagoras or finding the length of the vector MP. So think about it yourself and find the equation of a sphere, write it down, stop the film, and here comes the result. And the equation of the sphere looks exactly the same like that of the circle, except for having additionally z minus zm squared, so the coordinate z is being added. Solve example 4 on your own, stop the film, here comes the solution. The solution is very similar to the solution in example 1, so insert the coordinates of point M in this equation. We get here the equation of the sphere, then we want to find the r squared, r being the distance of M and P. We can either use the length of the vector MP or just insert the coordinates of the point P in here. In both cases we'll get exactly this equation. Solving that, we get that the radius r is 3, and hence the final equation for the sphere is this here. So let's move to example 4b. When we intersect the line with a sphere, we get either 2 points or 1 point if it's a tangential line, or we get no point if it's just passing aside the sphere and not intersecting with it. Think for a moment on your own how you would solve it. You may start it or you can try to solve it completely. And then here comes the solution. The principle is exactly the same as when intersecting a line with a plane. So intersecting a line with a sphere, we take the x-coordinate given by the line, so minus 3 plus 3t, and insert it for the x-coordinate in the equation of the sphere. We do the same with the y-coordinate, which is just t, and the z-coordinate is 4 minus 4t, so the z plus 2 becomes 4 minus 4t plus 2 squared, and now we have to solve this equation. The equation simplifies to t squared minus 3t plus 2 equals 0, and hence the solution t1 equals 1 and t2 equals 2, and inserting that into the equation of the line, we get these 2 points q1 and q2. In example C, we should find the tangential plane T to the sphere S at point q1. The tangential plane is obviously normal to the line mq1, so we can use the vector mq1 as a normal vector of the tangential plane. So we find the normal vector 2 minus 1 minus 2, we get the equation for the plane 2x minus y minus 2z plus d equals 0. Inserting the point q1 into the plane t, we get d equals 1, and hence we get this final result for the tangential plane. The second task is to find the angle of intersection of the line L that cuts somehow through this sphere and the sphere here at this point. And this angle of intersection is defined as the angle of intersection between the line and the tangential plane. And the angle between the line and the tangent is 90 degrees minus the angle between the line and the normal, as we have seen before. Well, the angle between two lines is found as the modulus of the scalar product of the two direction vectors divided by the product of the length of the two direction vectors, and we get that the cosine is 13 divided by square root of 26 times 3. And we get for the angle between the line and the normal approximately 31.8 degrees, and the angle between the line and the sphere is approximately 58.2 degrees. In example 5, we want to show that this is the equation of a sphere, and we will do it by bringing it into the form of the equation of a sphere. Think about it for a moment how this could work, and you can try it on your own, or just watch now the solution. Here it comes. Let us add 9 on both sides so we get the constant term to the right side. And then we rearrange the terms on the left side so that first we have the x squared, then the x's, then we have the y squared, then the y, here there are none, then the z squared, and then the z, and always leave a little bit of space before the next variable appears. In the next step, we want to transform this equation here, the left side, into the desired form. So we know this has to become somehow x minus something squared. Here we want y minus something squared, and here's z minus something squared. Since this is x squared minus 4x, the number that I have to fill in here has to be the 2, so I get the minus 4x. However, x minus 2 squared is x squared minus 4x plus 4. This plus 4 is here missing, so I'm adding it, so I have to add it on both sides. Now let's do the same thing for the y squared. Well, here there are no y, so it's just y minus 0 squared, or just the y squared that remains. And for the z squared, well, I have to get z squared plus 12z. This means I have to insert here plus 6. And z plus 6 squared is z squared plus 12z plus 36. So here plus 36 is missing. I have to add it on both sides. Well, and now my right hand side has become 49. Now we see this is indeed a sphere with center M2, 0, minus 6 and radius 7. Read example 6 and try to solve it on your own. So stop the film now, and here comes the solution. The radius corresponds to the distance of the point M from T, so we have to find an arbitrary point A on T, for example 0, 0, 4, and we find that the radius is 6 units. In task B, we have to find this point Q, where the tangential plane touches the sphere, and since we have to find that point Q, it turns out it would have been simpler to find it first and then solve A, with the radius being just then the distance MQ. To find this point Q, we have to intersect the normal to the plane T through M with the plane T itself. The equation of the normal is r vector equals the position vector of point M, 6, 5, minus 3, plus T times the normal vector we get from here, 1, minus 2, 2. We get Q as the intersection of N and T, and we get that T equals 2, and the point Q is 8, 1, 1. We are looking in C for tangential planes that are parallel to this plane, so we know their normal vector, 2, 2, minus 1, and so we know where they have to touch the sphere, namely where the normal through the center of the sphere intersects with the sphere. So the equation of this normal to these tangential planes is r vector equals, and now the position vector is the position vector of the point M, and its direction vector is this normal to the plane P, so 2, 2, minus 1. And let us now intersect it with the sphere. To find the equation of the sphere is rather simple. We know the coordinates of the point M, the center. We can insert them in here, and we know also that the radius is 6, so we can insert it here on the right hand side. Intersecting the normal with the sphere, we get this equation, and it simplifies. T squared equals 4 in the end, and when we take the root, we get for T plus or minus 2. Using T1 equals 2, we get this Q1. Both tangential planes have this equation since they're parallel to P. Now we know that Q1 is element of T1, so insert the coordinates of Q1 in here, and we find that it's minus 43, so we get the equation of T1, 2x plus 2y minus z minus 43 equals 0. Inserting for t this value minus 2 and proceeding the same way like before, we get the second tangential plane T2. Now read example 7 and try to solve it on your own. Stop the film, and here comes the solution. The center of the sphere is the point on L that has same distance from A and B. And this is a task that we have solved several times. Take the midpoint of A and B. The simplest way to solve this is to look for the point M on line L such that the vector MABM is perpendicular to the vector AB. Since the center of the sphere lies on the line L, we can write its coordinates in this way. The midpoint AB has these coordinates. We get them by taking the average of the x coordinates, the y coordinates, and the z coordinates of A and B respectively. And now we want MABM vector to be perpendicular to the AB vector. So the scalar product of the two vectors has to be 0, and we get t equals 2, and hence the midpoint m of the sphere has coordinates 7, 16, minus 9, and we have to find the radius now, which is just the length of the MA vector, which is square root of 5 squared plus 16 squared plus 13 squared, since this is the MA vector. And we get square root of 450 for the radius, and so we get the equation of the sphere, this here. Note that the 450 is just the square root of 450 squared. In example 8, please first correct the wrong y coordinate of the direction vector of the line L. The example 8 is sort of a wrap-up of many things that we have done in this whole vector geometry chapter. Read now example 8 and reflect how to solve task A using the 3 different methods as mentioned. Just think about it for a moment without really performing the calculations. Stop the film now. And here comes the solution. And I don't think it makes sense to write down all the details. Just write down the idea and then the main steps and the solution. Since the point Q lies on the line L, we can write its coordinates in this way. In A1 we should use the distance formula. The distance between points A and Q can be calculated as the length of the AQ vector, and so we can set the length of AQ vector equal to the length of BQ vector, or to simplify our life we'll set the square of these lengths equal. Using the coordinates of point Q and A, we get this vector as AQ vector, and with the coordinate of B, this vector as BQ vector. Calculating the squared length of these two vectors, we get this equation. When expanding it, we get this long equation, and solving it for t, we get in the end that t equals minus 6. And inserting that value here, we get q is 20 minus 70. In method 2, we have to use the mid-normal plane, so we need the midpoint of A and B, and the AB vector, which is the normal vector of the plane. We use that one to find the equation of the plane, and then we insert the midpoint into this equation and find that D is minus 19, and we find in that way the equation of the plane. And then we have to intersect the line L with the plane. We find again T is minus 6 and the same Q as before. The third way is the simplest way to solve the task. Just let's find the point on the line L, Q, such that MQ vector is perpendicular to AB vector, M being the midpoint of A and B. When we get MQ vector scalar AB vector has to be equal to 0, and again we find T equals minus 6, and we'll get the same Q as before. Now read the 5 tasks in part B and think for each of them how to solve it. And as I say, think about it, don't do any calculations, you should realize something. Please stop the film, really think about it before you look at the solutions that I will provide here now. All tasks are equivalent to that in A, so the solution is always Q has coordinates 20 minus 7, 0.